So what exactly do these two types, stripping and spray, what do they actually do?
Yeah, it's fascinating because they have these dual but very distinct jobs. So stripping, think of that as getting the absolute last drops out. After the main cargo discharge, you use these pumps to remove the final quantities of LNG from the tanks. It sounds simple, maybe just efficiency, but it's more than that. It stops residual cargo building up over time, maximizes how much you actually deliver, and critically, it gets the tanks ready if you need to do maintenance or inspections. I mean, imagine trying to send someone into a tank with even a little bit of that highly flammable gas left. It's a complete non-starter. Then on the flip side, you have spray operations. This is different. Here, you're circulating a small amount of LNG inside the cargo tanks using special nozzles. It's not about emptying, it's about managing the environment within the tank. It cools the tank structure itself, helps manage the pressure and temperature of the main cargo body, and crucially, it minimizes how much boil-off gas, or BOG, you get during the voyage.
BOG, boil-off gas.
Exactly. And BOG is basically cargo evaporating. It's lost product, lost energy, lost value. So effective spraying directly preserves the cargo.
Right. So if BOG is a direct hit to the bottom line, that need for precision, it starts to make more sense. But why does it demand such, specialized engineering? Why are these pumps designed to such almost extreme standards for tasks that maybe on the surface sound straightforward?
Well, it really boils down to the fundamental physics you're dealing with, cryogenics. These pumps are designed very specifically to operate inside the cryogenic liquid itself. They live in it. The most common type you'll find are submerged motor pumps. And what that means is the electric motor isn't outside somewhere connected by a long shaft, like you might imagine. No, it's actually integral to the pump unit. The whole thing is immersed in the LNG cargo.
Wow, okay.
This design is clever because it gets rid of the need for complex shaft seals that would otherwise have to bridge that huge temperature gap between -162°C and ambient. That was a massive problem with earlier designs, the old deep well pumps. A huge leap forward, really. And to handle those, frankly, brutal conditions, the materials have to be spot on. The pump casing, the impeller, the motor housing, they're typically made from specific types of austenitic stainless steels, like AISI 304. These aren't just any stainless steels. They're chosen because they keep their strength and, crucially, don't become brittle at those incredibly low temperatures.
Right, because regular steel would just shatter.
Right, glass, exactly. So material science is absolutely key here.
That's incredible. So the cargo itself is bathing the motor, keeping it, well, not cool in the usual sense, but stable at -162°C. But when you're actively pumping a liquid that's already right at its boiling point, what kind of thermodynamic nightmares does that create?
That's precisely the challenge, yeah.
Yeah.
The thermodynamics are critical. As you pump the LNG, the pressure naturally drops a bit as it goes through the pump. If that local pressure dips below the LNG's vapor pressure, remember it wants to boil, you get problems. Specifically, flashing or cavitation.
Cavitation, right. The bubbles forming and collapsing.
Exactly. And cavitation isn't just noise. It's the rapid formation and violent collapse of vapor bubbles. It can physically erode and damage the pump's impeller and casing over time, and it kills efficiency. So maintaining enough pressure at the pump's inlet is vital. That's what we call net positive suction head, or NPSH. You need enough push to keep it liquid. And think about this too. Even the heat generated by that submerged motor and the friction inside the pump has to go somewhere. Where does it go? Into the LNG flow itself?
So it slightly warms the cargo?
Just a tiny bit, yes. Which contributes a little to BOG. So an efficient pump design is also one that minimizes this extra heat input. It's all connected.
So we've moved from, simpler, maybe more exposed pump systems in the past to these highly integrated submerged units. That evolution sounds like it must have been quite a journey. What were some of the really big engineering hurdles in making them so, integrated with the whole ship's cargo system?
You've hit it right there. The integration was the huge challenge. Moving from thinking about separate components to designing a truly cohesive system. Early systems were definitely more segmented, but today, these submerged pumps are intrinsically linked to everything. The cargo tanks, obviously, but also the miles of piping, the complex reliquefaction plants that capture and re-chill the BOG.
Right, turning that lost gas back into liquid.
Precisely. And the sophisticated vapor management systems, too. It's not just a pump dropped in a tank anymore. It's like a central node in the cargo's nervous system. Getting all these parts to talk to each other, operate seamlessly, reliably under these extreme conditions. That was, and still is, a continuous engineering refinement over decades.
Okay, so with all this incredibly sophisticated engineering, it follows that the operating procedures must be just as precise, just as meticulous. For the operator on board, what are the absolute must-do, the golden rules, before you even think about pushing the start button on one of these pumps, especially if it's been sitting idle and warmed up?
Oh, absolutely. Rigorous protocols govern everything. And the most critical first step, the one people sometimes rush, is the cool down process. If that pump has warmed up, say during maintenance or a ballast voyage, the tank itself needs to be cooled down first to at least 130 degrees Celsius. Then, the pump unit itself has to be fully submerged. You need at least 1 meter of LNG covering it. And here's the real kicker, the vital step. You absolutely must allow for a soaking period of at least 1 hour with the pump fully submerged before you attempt to start it.
1 full hour, just soaking.
1 full hour, minimum. It's not optional padding. It ensures the entire pump assembly reaches thermal equilibrium with the LNG. Skipping this or cutting it short induces massive thermal stresses across the pump components, metal contracting unevenly. That's how you get damage, seizures. It's critical for longevity.
That 1 hour soak really underscores the thermal challenge. Okay, so pump's cooled, it's soaked. What's next on that pre-start checklist? Are there specific steps that often get missed or maybe misunderstood?
Right. So once it's properly cooled and soaked, the pre-startup checklist kicks in. You need to confirm the liquid level in the tank is sufficient. The minimum is technically 350 millimeters, but the ship's safety system, the interlock, usually demands more like 1.3 meters as a safety buffer. Much safer. You also check the tank pressure needs to be above 30 millibars gauge pressure, positive pressure. And here's a really crucial one, often misunderstood. You have to manually set the pump's discharge valve to 20% open before starting. You do this via the ship's control system, the IAS.
20% open, that seems very specific.
Yeah.
Why not fully open? Or why not start against a closed valve, which is common for some other pump types?
Great question. And it goes right back to that core principle we talked about. Remember, the LNG isn't just the stuff you're moving. It's also the coolant for the motor windings and the lubricant for the pump and motor bearings.
Right, the dual role.
Exactly. If you start against a fully closed valve, you have zero flow. Zero flow means zero cooling, zero lubrication. The pump might start spinning, but it immediately risks overheating, excessive vibration. You'll wreck the bearings and seals incredibly quickly. Mechanical damage is almost guaranteed. Starting fully opened isn't ideal either, could cause a surge. That 20% provides just enough initial flow to establish cooling and lubrication without overloading anything. It's this dual-function cargo and lifeline that makes following procedures absolutely non-negotiable. And once it is running, you have to stay within its designed operating window. There's a minimum continuous flow rate, usually around 18.2 cubic meters per hour. You need to keep things cool and lubed. And then there's the rated capacity, maybe 50 cubic meters per hour. Going below the minimum or drastically exceeding the rated flow will cause damage. Those numbers define its safe zone.
Okay, so the LNG is cargo, coolant, lubricant, and it's incredibly cold and flammable. Safety isn't just a procedure. It sounds like it's woven into the very design and operation. What are the biggest inherent risks you're constantly managing? Maybe some that aren't immediately obvious, and how do the layers of protection work?
Well, the systemic hazards are always there. You've got the risk of overpressurization. Say if liquid gets trapped in a line and starts to warm up and expand, that's dangerous. We've talked about cavitation causing mechanical damage. That's a constant concern. And of course, any leakage of LNG is a major hazard. Fire, explosion risk, plus severe frostbite if it contacts skin. So to counter these, vessels have multiple layers of defense built in. You have alarms for early warnings of abnormal conditions. You have interlocks, which are automated safety functions that prevent unsafe actions.
Like preventing a start if a valve isn't open.
Exactly that. Preventing pump start if suction valves aren't fully open, for instance. And then you have emergency shutdown systems, the ESD. These provide a rapid, controlled way to stop operations if something goes seriously wrong. And all of this is designed and operated under very strict international rules, like the IMO's International Gas Carrier Code, the IGC code. But beyond the hardware, we really need to bust some dangerous myths, some misconceptions. The first, and maybe the most dangerous, is thinking, it's just another pump.
We've heard that one before.
Right. And it's absolutely not true. As we've, hammered home, that's the submerged motor design, the LNG being coolant and lubricant. It's unique. Deviate from the procedure, you risk catastrophic failure. It's not forgiving. The second big misconception, these alarms are just annoying background noise.
The alarm fatigue issue.
Precisely. But no, those alarms are your critical safety nets. They are telling you something important, like a low motor current trip, an undercurrent, say at 15 amps for 10 seconds. That usually means the pump has lost suction, it's running dry. That alarm is saving the pump from destroying itself through cavitation. Or a high motor current trip, Overcurrent, maybe 35 amps. That signals an overload, maybe a blockage, something preventing it from turning freely. Understanding what each specific alarm means, why it's activating, that's fundamental. It's the pump communicating distress. I recall one instance where recognizing that specific 15-amp undercurrent trip allowed an operator to stop immediately, preventing severe cavitation damage that would have meant weeks of downtime. They're not nuisances. They're vital diagnostics.
That's a really powerful point. Those alarms aren't just warnings. They're giving you specific diagnostic information if you know how to read them. So, okay, things won't always go perfectly. How do you move beyond just reacting when an alarm goes off to proactively understanding the pump's health and optimizing its performance using all this data?
Yeah, this is where you shift from just following procedures to really mastering the system. Common problems tend to fall into a few buckets. You've got mechanical issues, things like vibration, maybe from an unbalanced impeller, or even seizure. If the cool down wasn't done properly, you get cryogenic issues, thermal shrinkage causing misalignment, or maybe even ice forming inside if moist air somehow got into the system.
Ice and Negus 162C, that sounds bad.
Very bad. Locks things up solid. And then you have instrumental issue sensors drifting out of calibration, control system glitches. So to optimize, you first need to measure and, more importantly, interpret what you're measuring. These pumps talk to you through their key performance indicators, the KPIs, which you see on the integrated automation system, the IAS. Take discharge pressure. If you start the pump and the pressure is near zero, or maybe 75% lower than usual, that's a classic symptom. It often means reverse rotation wired backwards after maintenance, perhaps, or it's lost suction completely. And the system's smart. If that pressure stays below about 0.2 megapascals for 10 seconds, it'll shut the pump down automatically to protect it. Then look at motor current, a healthy start. You see a brief spike as it overcomes inertia, then it settles down nicely within about 3 seconds. But if that current stays high for more than, say, 10 seconds, big red flag. That could be a locked rotor, maybe it is iced up, or an electrical fault like single phasing. You stop immediately, manually. And conversely, that undercurrent trip we mentioned, 15 amps for 10 seconds, that's the pump screaming that's running dry.
Critical protection. And vibration levels. Okay, this might not always be a precise number on the screen, but any noticeable increase, any unusual noise, especially if you made the mistake of starting against a closed valve, it's immediate mechanical stress. You feel it, you hear it. Trust your senses too. These aren't just numbers or status lights, they are direct diagnostic clues.
Right, so it's about pattern recognition almost. Understanding what normal looks like for that specific pump, and then spotting the deviations and knowing what they likely mean. How does an experienced operator use this data stream not just to fix problems, but to get ahead of them, towards predictive maintenance?
It's exactly that. Predictive, not just reactive. This is where diligent data logging comes in. Systematically collecting this data, creating a performance log for each pump, establishing its normal baseline when healthy. Then you can spot subtle trends over time. Is the current gradually creeping up? Maybe bearings are starting to wear. Is efficiency slowly dropping? Perhaps impeller erosion. This analysis transforms you from just being a system user to being a system manager. You can schedule maintenance proactively before a minor issue becomes a major costly failure. It's about anticipating. And for the really seasoned operators, there are even more advanced techniques. For example, fine-tuning the undercurrent relay setting. This involves carefully adjusting it, balancing between the pump's no-load current and its typical operating current to get the most sensitive protection without nuisance trips. It requires deep knowledge of that specific pump. And in really rare extreme cases, like a confirmed suspicion of an iced-up pump, that locked rotor scenario, there's a high-stakes procedure called a reversed rotation test.
You intentionally spin it backwards.
Briefly, yes. Performed only by qualified personnel, following incredibly strict electrical safety lockout procedures.
Yeah.
The idea is a quick reverse bump might just be enough to crack the ice and free the rotor. But let me stress, this is an emergency measure, a last resort, not routine troubleshooting. It highlights just how crucial deep system understanding and absolute procedural discipline are.
That's fascinating, almost like pump surgery in extreme circumstances. So looking forward then, with all this complex tech already in place, what's the next horizon for cryogenic pumping on these vessels? Where's it heading?
I think the trend is definitely towards more integration, more digitalization, more automation. We're talking about more sophisticated control algorithms that can adapt pump operation dynamically to changing conditions in real time. Predictive analytics based on machine learning that can forecast potential failures with even greater accuracy, weeks or months in advance, and eventually, maybe even elements of AI for self-optimizing pump operations, constantly fine-tuning for maximum efficiency and reliability. Understanding these fundamentals we've discussed today, that's really the foundation for engaging with that smarter, more predictive future in maritime operations.
Wow, okay, what a fascinating deep dive that was. We've really covered some ground. From the sheer physics of handling liquids colder than Antarctica down to the critical detail of why you wait 1 hour for a pump to soak. Understanding the why behind that specific 20% valve opening and decoding what the motor's current draw is actually telling you, it's clear these aren't just background machinery. These pumps are absolutely central to the safety, the efficiency, and the environmental performance of LNG transport. And they directly hit the bottom line for every single cargo. So for you listening, the path to really optimizing performance here seems clear. It's about embracing advanced condition monitoring tools. It's about continuous investment in crew training, not just the basics, but deep troubleshooting for these complex cryogenic and electrical or control system faults. And it's about leaning into digitalization for smarter, maybe more automated control and oversight. Proactive maintenance, always, not just reacting when things break. So here's something to chew on. We've talked a lot about LNG's unique dual role. It's the valuable cargo, but it's also the essential coolant and lubricant keeping the pump alive. Thinking about that unique relationship, how might that insight make you look differently at any critical system where the substance being handled is also fundamental to the machinery's own protection and operation? Something to consider. Keep digging, keep learning. Thanks for joining us on this deep dive.